Hey there, it's Shannon Matchick-Myers, and today we'll be checking out section 15.1, vector fields. So we'll be starting vector analysis. Very, very exciting. So we'll be looking at the concept of a vector field, determining whether a vectored field is conservative, finding the curl of a vector field, and finding the divergence of a vector field. So let's warm it up by looking at this problem. A 48,000-pound truck is parked on a 10-degree slope. Assume the only force to overcome is that due to gravity. So we want to first find the force required to keep the truck from rolling down the hill, and then find the force perpendicular to the hill. So I think this was somewhere in chapter 11, but if you want to look back, or if you remember that, that's cool. Otherwise, you can work it with me. So I know you can do it. Go ahead, warm it on up. On your mark, get set, go! All right, let's see how you did. So what the heck do we have going on here? I mean, we've got this, 10-degree slope, something like that, right? And then there's a truck on it. Actually, all right, so we've got, our trucks on there, something like that. And here, that angle is 10 degrees from the horizontal, all right? And we've got our truck carousing around on here with hopefully the wheels on the on the street. And he's got his little window there. And the wheel's probably a little further up. All right, so we've got our beautiful truck here. And so here, if we take a look at what we have going on, if we call this right here vector V, right? And vector V, of course, will be equal to cosine 10 degrees I plus sine, and I is a vector, sine 10 degrees J. And we're also going to have to figure out, we've got this gravitational force, right? That's hitting down, so we need to know that. So that is gravity pushes down, so that's going to be negative 48,000, and that's J because it's going up and down, and that's due to gravitational force. All right, and then so let's see what we have going on. So the way to find the force required, right? Because that was gravitational force. So the force required to keep the truck from rolling down the hill, right? Let's call that W1. You might not remember that. And that's going to be the gravitational force, dot V divided by the magnitude of V squared times v, right? And that will end up being, well, the magnitude of v is just 1, right? So we'll just have f dot v times v, and then that will be equal to, so f dot v is going to give us what? So we have 0, negative 48,000 dot cosine 10 degrees, sine 10 degrees. And then we're going to multiply that to v. I'm just going to write it as v right here. Until we have our dot product. And then what will we get? Well, the first part will zero out. And then we'll have negative 48,000 times sine at 10 degrees. And that will be and let's see what mode I'm in. I'm in radians, so we'll get to degrees. And that's negative 8,335.1. And then that's going to be times v, which was cosine 10 degrees, sine 10 degrees. Now, we're going to want the magnitude of W1 in order to figure out, the magnitude of W1 is the force required. So the magnitude of W1 is going to equal to the absolute value of the constant, right? Negative 8,335.1 times the square root of cosine squared at 10 degrees plus sine squared at 10 degrees. But isn't that just 1, right? So square root of 1. So the force needed to keep the truck from on the road there, from rolling down the hill, is going to be 8,335 approximately pounds. Cool? All right. So then, now we want to find the force perpendicular to the hill. So the force that's perpendicular to the hill is, remember that W2, the magnitude of W2 is what we're looking for. So that is just equal to the magnitude of F minus W1. And so that would be the magnitude of negative 48,000 J was F. And then minus W1 had, remember we had, actually we can say plus 8,335.1 times cosine 10 degrees I plus sine 10 degrees J. But what happens again is that we'll end up with, well, let's see what we get for a vector. So here we would end up with, and this is approximate since we had rounded the 8335.1. So let's see what happens. This will end up being the magnitude of So let's see, 8335.1 times cosine 10. All right, so we get that for the I component, and then the j component will be negative 48,000 plus 8335.1 times sine 10. And so that's our j component, approximately 8208.5 I think it was, and then minus 46,552.6 times j, square root of 8208.5 squared. I'm just going to add, that negative will go away when I do this. 46,552.6 squared, enter, and we get approximately 47,270.8. And that is in pounds. Groovy? All right, so hopefully we're all warmed up. Now let's look at the definition of a vector field. If we let m and n be functions of two variables x and y defined on a plane region R, the function f, and that's a vector f, it's a vector function, vector valued function f defined by f at x and y equal to m times I, the vector I, plus n times the vector j, is called a vector field over R, and that's in the plane. So similarly, if you've got m, n, and p are functions of three variables x, y, and z defined on a solid region Q, so the function, vector valued function f defined by f at x, y, and z is m times the vector I plus n times the vector j plus p times the vector k, and that's called a vector field over Q in space. All right, so looking at our next example, let's look at this one. Sketch several representative vectors in the vector field f at x and y is xi minus yj. So here, let's take a look at this. The magnitude of f is equal to the square root, of x squared plus y squared, right? And the magnitude of f is equal to some c. And so wouldn't that be true, that you'd have x squared, putting it together, plus y squared would equal to some c squared. Well, what would happen? I mean, at the point 0, 1, right? What would your vector end up being? Your vector would end up being, well, 0i, it would be 0i minus 1j, right? So that would be negative j. And so that's negative 1j, right? So it's the point 0, 1. Your vector, right, would be pointing down, and it would go down like this. Cool? Right? And then for the point 1, 0, you would just have I, and so do you see your vector would go like this. It would be length 1, and it would go out like that because it's positive. And if you were at negative 1, 0, you'd have negative I, and so you'd be going like this, And if you had 0, -1, so you'd be starting at 0, -1 and then going up. So it'd look like this. So let's just do a couple. What if you were on the next circle, right? And you'd be, what was that one that I did? 1, 2, that had a radius of 2. And so you'd have an ordered pair at 2, 0, right? And so the magnitude of that's going to be 2 now, right? And so if you're at 1, 2, 0, your magnitude's going to be 2. You're going to have 2i as your vector, right? And so you'd be here and you'd be going out 1, 2. I think I screwed up that scale. I think it's going to be 4 actually. Sorry, my bad. This will be 4 on this ring, and so then we'd have. So if you're at 2, 0 and you're working on this circle, you'd be going to the right 2. Make sense? And then if you were at pi over 4 on this circle, you'd be what? You'd be like over here, right? And so what would your length be then? You'd end up with a vector that's pointing down here to 4. Pretty cool, huh? And then, similarly, if you're up here, you'd be pointing down to here. Pointing up to, pointing this way. And if you continued around over here. Anyway, pretty groovy, huh? All right, and you could continue on, but that's just some representative vectors in that field. All right, so let's take a look at this one. If you've got the vector field f of x, y, and z is xi plus yj plus zk, what's going to happen is you're going to have when you're looking at your magnitude of f, right? You're going to end up with the square root of x squared plus y squared plus z squared. And then the magnitude of f would also be some c. And then you'd end up with x squared plus y squared plus z squared is c squared. So you'd have spheres, right? So if we make a sphere, square root it. Okay, I guess I got lazy, sorry. I wanted to save some time here. All right, so then what's going to happen here is it's pretty cool. These are going to go, they'll just be going up, right? What's their magnitude going to be? Hang on. So if this is for C equal to 1, right? So if we look at the points and the vectors, so if you've got 0, 0, 1, and you've got x squared plus y squared plus z squared is 1, and then the vector would be what? Because we started out with what? xi plus yj plus zk, right? And so, sorry, I think I'm diverging a little bit. So here, if we, that would just be k, right? The vector k. And it would have a magnitude of 1. So it would go up here. And similarly, they will all kind of go out like that. Pretty cool, huh? Awesome. All right. So anyway, that is that one. So I was just drawing in the other ones, but if you had, 1, 0, 0, you'd have the vector I, right? If you had 0, 1, 0, you'd have the vector J. And we're looking again at this. And if you had the vector, let's see, -1, 0, 0, you'd be at -I. And if you were at 0, -1, 0, you'd be at -J. And 0, 0, -1, you'd be at -Z. So those are the ones I drew. Groovy? All right, so definition of an inverse square field. So it turns out that if we let r at t, that's another vector valued function, equal to x at t times I plus y at t times j plus z at t times k be a position vector, the vector field F is an inverse square field if F at x, y, and z is equal to some constant over the magnitude of r squared times a vector u, where k is a real number and u is equal to r divided by the magnitude of r as a unit vector in the direction of r. Groovy? All right, definition of a conservative vector field. A vector field F is called conservative if there exists a differentiable function f such that this f, the vector f, is equal to the gradient of f, or del f. The function f is called the potential function for the vector field f. All right, so example 3, let's find the gradient vector field for the scalar function. So that is, another way to say it, find the conservative vector field for the potential function. So we have f of x, y, and z equals to y over z plus z over x minus xz over y. So, well, let's find del f, right? If you recall, that's going to be the first partial with respect to f times I, or with respect to x times I, first partial of f with respect to x times I, plus the first partial of y with respect to y times j, and then plus the first partial of f with respect to z times k. And we're saying that is going to equal to our vector field f at x, y, and z. Cool, cool? So, let's do it. Fx at I is going to be what? That middle term will be So remember, we're treating everything as a constant except for x. So that's like zx to the negative 1. So we would end up with negative z over x squared. And then we would have minus z over y. All that times I. And then the first partial of f with respect to y is going to be, let's see, we'll have 1 over z. Second term doesn't have any y's. And then minus a minus is plus, so we would have plus xz over y squared times j. And now, first partial of f with respect to z. Z's in everything, isn't it? So we would end up having plus negative y over z squared plus 1 over x minus x over y times k. And that is our vector field, or our that's our conservative vector field for the potential function. So f x, y, and z equals okay. So here's a theorem, a test for the conservative vector field in the plane. All right, so let M and N have continuous first partial derivatives on an open disk R. The vector field given by F at x and y equal to Mi plus Nj is conservative if and only if, so this is a two-way proof, or a two-way relationship, if dn dx is equal to dm dy. So you want to figure out what's your n and what's your m and what's your n, right? And so remember that whatever the coefficient to I is your m, and the coefficient to j is your n. So let's take a look at this. So our capital F at x and y is equal to 1 over y times I, and then I'll just add, and then we'll have negative 2x over y squared times j. So m is equal to 1 over y. N is equal to negative 2x over y squared. And so now let's figure out what we have going on. So dm dy is going to be beautiful negative 1 over y squared, and dn dx is going to be negative 2 over y squared. So the vector field is not conservative. Good so far? All right. Okay, so definition of a curl of a vector field. So the curl of the vector field f at x, y, and z equal to mi plus nj plus pk is del cross f at x, y, and z. And so if you remember cross product, it comes from well, we might as well write it out. It comes from the determinant. You'd have I, j, and k. You would have ddx, ddy, and ddz. And then you'd have your m, your n, and your p. And then you would find that determinant, which happens to be what you see here. Okay, so actually I said del. I should have said probably delta. Anyway, that's no, not delta. The del is representing the differentiating operation. So let's find the curl of f for this vector field. F at x, y, and z is e raised to the negative x, y, and z times I plus j plus k at the point 3, 2, 0. So do you see, fortunately, that m equals n equals k, right? Or not k, equals p, because that e to the negative x, y, and z is factored out, so that they're all equal to e to the negative x, y, z. So dm dy is going to equal to negative negative xz e to the negative xyz dm dz is equal to negative xy e to the negative x, y, and z and then dn dx is going to equal to negative yz e to the negative xyz dn dz will equal to negative xy e to the negative xyz. And then we need to do p, so dp dx will be negative yz e to the negative xyz, and dp dy will be negative xz e to the negative xyz. Cool, cool? All right, so here we go. The curl, so here now we just need to plug everything in, right? So the curl of this vector field f of x, y, and z is equal to, so dp dy, where was that one? So we'll have negative xz e to the negative xyz minus, so it'll be a plus because they're all negative, so dn dz was, we'll have xy e to the negative xyz, that's times I, and then minus dp dx was negative yz e to the negative xyz, minus minus is plus, so then we'll have dm dz, so xy e to the negative xyz, that one is times j, and then plus dn dx will be negative yz e to the negative xyz, plus, because remember there's a minus in the formula and they all have negative coefficients, so dm dy will have our xz e to the negative xyz, and that's all times k. So at 3, 2, 0, we could definitely simplify this, but we're evaluating it anyway, right? So the curl evaluated the curl of f at, what was it, 320 is going to be, so that's going to mean that the exponent on all the e's is going to be 0 because 3 times 2 times 0 is 0. So that simplifies all of those. So then we'll end up with, let's see what we end up with. So for the first term, we'll have, that'll zero out. Anything that has a z zeroes out. So then we'll end up with 6. So this one, actually I'll just kind of go here. This one will end up getting 6 because 3 times 2 times 1. This one will zero out. This one will zero out. This one will be 6. This one will zero out, and this one will zero out. And so we'll end up with, let's see, 6i minus 6j, and then the k zeroes out. Groovy? All right, so now we're on a theorem, test for conservative vector field in space. So here we go. Suppose that M and P have continuous first partial derivatives on an open sphere Q in space. The vector field given by f at x, y, and z equal to m times I plus n times j plus p times k is conservative if and only if the curl of f at x, y, and z equals the zero vector. So that means that for it to be the zero vector, dp dy has to equal to dn dz, right? And notice these are going to match. These are going to match. So basically, the things being subtracted as the coefficients to I, j, and k have to zero out in order to get the zero vector, right? So that's where we get all of this. So dp dy has to equal dn dz, dp dx has to equal dm dz, and dn dx has to equal dm dy. All right? So here we go. In example 6, we have determine whether the vector field is conservative, and if it is, find a potential function for the vector field. So we've got f at x, y, z equals y squared times z cubed times I plus 2xyz cubed times j plus 3xy squared z squared times k. So here we go. First of all, find out if it's conservative, because if it's not, we won't need to go on. So here we go. Is dp dy equal to dn dz? So remember that for this one, m is equal to y squared times z cubed. N is equal to 2xy z cubed. And p is equal to 3xy squared z squared. All right, so dp dy, let's see, is going to be 6 xyz squared, and dn dz would be 6xyz squared. Check. All right, so then is dp dx, is that equal to dm dz. Well, dp dx is going to be 3y squared z squared. And dm dz will be 3y squared z squared. Looking good so far. Check. And then lastly is dn dx. Is that one equal to dm dy? So dn dx will be 2yz cubed. dm dy is 2yz cubed. So we're good to go. So F is conservative. So let's check this out. Consider f at x, y, and z. Equal to the integral of m dx. Well, what would we get? We'd end up getting the integral of y squared z cubed dx, right? Which in turn would be x y squared z cubed, and then you'd be adding some function g of y and z. Okay? Alright, well, f at x, y, and z, if you took a look at integrating in with respect to y, well, we'd have the integral of 2xyz cubed, right, dy, which in turn would be, so what would that be? Y squared over 2, so the 2 would divide out. So we would have xy squared z cubed plus some function h of x and z. Well, looking at, bet you guess what I'm doing now. If we integrate p with respect to z, right, well, we'd be integrating 3xy squared z squared dz. And so that would end up being, what will we get? The 3 will divide out, so we'll have x y squared z cubed plus some other function k, and that would be in terms of x and y. So g of y and z equal to h of x and z equal to k of x and y. Let's just call this some capital K, not the vector K, some capital K. All right? So therefore, f at x, y, and z equal to, and the reason they're all equal, of course, is because we got the same, antiderivative, for each of them. Notice, we got the same result. So that's why if we set the constants equal to, those functions equal to each other for some k and call it some k, then we would have x y squared z cubed plus k is a potential function for the vector field f x, y, and z. Cool. Cool, cool? All right, now we're on divergence of a vector field. So the divergence of f at x and y equal to mi plus nj is denoted divergence f, so div f x and y is equal to that, differential operator dot the vector field f at x and y. Sorry, this is a vector. And that is dm dx plus dn dy. And similarly, if we're in 3 dimensions, we'll have divergence of f of x, y, and z will be that differential operator dot the vector field at x, y, and z, which is, and notice, because we're doing a dot product, we're going to end up without vectors. We don't have vectors at the end. So dm dx plus dn dy plus dp dz. If the divergence of that vector field is 0, then f is said to be divergence free. Okay? So example 7, let's take a look. Find the divergence of the vector field f at x, y, and z is natural log at x, y, z, all of that times I plus j plus k. So notice m will equal to n will equal to p at the point 3, 2, 1. So m equals n equals p equals natural log at x, y, z. So dm dx will be equal to yz over x, y, z, which will be 1 over x. dn dy will equal to xz over xyz, which will be 1 over y. And dp dz will be xy over xyz, which is 1 over z. Groovy? So the divergence of f in terms of x, y, and z is equal to 1 over x plus 1 over y plus 1 over z. And if we evaluate this at, what was it, 3, 2, 1, we will get 1/3 plus a half plus 1 over 1, which ends up giving us, let's see, 6. So we'd have 2 plus 3 is 5 plus 6. That would be 11 over 6. Cool, cool? All right. So the relationship between divergence and curl. So if your vector field f at x, y, and z equal to m times I plus n times j plus p times k is a vector field, and m, n, and p have continuous second partial derivatives, then the divergence of the curl of f and remember, curl of f is, vector. So that if the divergence of the curl of f is, that means it would be equal to 0, okay? If, of course, you've got your vector field and m, n, and p have continuous second partial derivatives. All right, so anyway, some interesting things for vector fields representing velocities of moving particles. The divergence measures the rate of particle flow per unit volume. In hydrodynamics, which is the study of fluid motion, a velocity field that is divergence-free is called incompressible. And in the study of electricity and magnetism, a vector field that is divergence-free is called solenoidal. So to try to bring some of the real world in there. All right, so here next time we'll be looking at line integrals. I hope you're having a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, please subscribe and tell your friends. Thank you. Bye.